So we're going to do more with piecewise functions. It's a harder topic, so we're going to spend 2 days on it. I'm going to add a little bit of vocabulary. We talked about continuous versus discontinuous. We're going to talk about 2 different types of discontinuities. But can we recall what discontinuous meant? It meant that the function was what? Like they broke, right? You couldn't trace it like without lifting your pencil off the paper. So types of discontinuities. We have removable and non-removable. And I'm just going to draw a little picture of each of them. So we're going to label our discontinuities as removable or non-removable. So mathematicians are not very creative people. Everything sort of is exactly what it sounds like. Removable means that you just removed the point. So it's going to look like a hole. Like you just took the point out. Now it could just be a hole, or sometimes what will happen is you'll have a hole and then the actual point will be floating somewhere else. Do you remember we did some like that last time where there was that like floating point? So one of those 2 situations is what we call removable. So you just like removed the point out of the graph. And you could make it continuous again if you could just put it back. So if you could put that point back, it would be continuous again. Non-removable is a more deep-seated issue. You can't reconnect it just by putting a point back in. So that would be something like what we call a jump, where it's like actually broken. You can't fix that just by putting a single point back in. You didn't just remove something, like it's actually broken. And we call that a jump discontinuity. Again, mathematicians aren't super creative. It jumped, we call it a jump, right? The other type that's non-removable is when you have a vertical asymptote. So your graph would do something like that. You can't fix that and make it connect again just by putting a single point back in. It's a bigger problem. So removable, you just removed a point. Non-removable is you can't fix it just by putting a point back in. So for 1 through 4. We'll do that. That'll be like the first half. We'll do 1 through 4, and that's what we'll split it to do our break. For the following functions, we're going to draw the graph, state domain and range, and then label our discontinuities. Okay. What is what I call a cut point for this one? Where's the cut point? Do you remember the flip book where we physically cut it? Cut point is not an official vocabulary word. That's a Miss Cole thing. I made that up, but it's getting split at 2. So here's where it's going to get cut. So let's do the first one. What will this graph look like? A U. And what's been done to it? Flips. It's going to be upside down and up 6. Good. Go up 6. We'll put a point. And we're expecting it to be upside down. And I'll just make a little table. If you can plug in numbers without drawing the table, like if you can do that in your mind, that's fine. A table is not a requirement. I just have found over the years that it helps people a lot to write one. So what number do you want to plug in? I heard 1 and I heard 2, and I agree with both of those. So let's do both of them. If you plug in, do you see, you're getting more confident with what you want to plug in. Comes from practice. All right, if you plug in 1 squared, 1, but it's -1 plus 6, 5. Good. So you get 1, 5, and then the symmetric point. And then we're going to plug in 2. 2 squared, 4, but it's -4 plus 6 is 2. So 2, 2, same thing on the other side. Now, when you connect it, just don't go past 2. You have to stay 2 or smaller, so it should look like this. And I left this a closed circle. Why did I make this closed at 2? Equal 2, good. And so it's like you just amputated the graph. And I hope I don't offend anyone when I say the graph got amputated. I'm not trying to be ableist. It's just a really good analogy for what we did. Like you literally just cut it off right there. All right, so we're going to have a different graph for everything bigger than 2. This one's going to be a line. It's linear with a slope of 1/2, up 1 over 2, okay? Now, I would still start by plugging in 2, and here's what I get all the time. You can't plug in 2. You can. You just have to put open circle. All right, so if you plug in 2, hey, guys, what's half of 2? 1. So 2, 1 gets an open circle. And then you can do this one of 2 ways. You can either make a table and keep plugging in numbers, or you can just go, oh, my slope is 1/2. So from there, you can go up 1 over 2, up 1 over 2. I think that's definitely a more efficient way, but if you want to make a table and plug stuff in, that will get you the answer as well. So it's whatever suits you. So we're going to do domain, range, and then we're going to state the discontinuities if there are. I'm going to ask you that. So domain, we're going to sweep left to right. Watch me point to this because I don't have better explanations for domain or range than here, look, okay? I know this looks like it's pointing down, but do you get that it's going to keep going left forever and ever and ever? Okay, so we have everything on the left and then everything on the right. Doesn't it keep on going? Now look here, because everyone's always like, but wait, what happened there? Doesn't this piece pick up where that piece left off? So as you scan left to right, do you lose anything? No. So your domain is everything. Negative infinity to positive infinity, parentheses, because you can't bracket an infinity. It's not a number, it's not a value, so you can't bracket that. Range, you're going to sweep downwards to upwards because it's smaller to bigger. Again, just watch me point to it. Does the graph go down forever? Yes. And then is this going to go upwards forever and ever off the paper forever? Yes. Now, everyone's always like, well, what about the whole? Well, didn't we pick up that value over here? Like if you ignore that part, as we sweep through, don't we get all the Y numbers? Yeah, so it's going to be everything. So I know it looked a little disjointed, but we still got it all. And the final question was continuous or discontinuous? What do you think? All right, discontinuous. And this is the thing I'm adding today. This is the new thing. Is it removable or non-removable? It's a jump. You can't fix it by putting a point back in. It's actually broken apart. So it's non-removable discontinuity, and you can abbreviate, at x equals, and you always have to say where. So it's non-removable discontinuity at x equals 2. Good. We're going to try it again. That removable versus non-removable is the new thing. So that's always tough. Ooh, this one has 3 pieces. Let's just look at the first one. What is just 4 going to look like? Constant. That's what I was looking for. Horizontal line at 4. And we're going to stop at -3. So this is like our cut point here. So you're going to have this flat line at 4. Stop when you get to x being -3, closed or open circle. Good, closed. So it should look like a clock hand. So -3 is our first cut point. All right, how about that middle section? What is that going to look like? A V. What direction did it shift? Up, down, left, right? It went right 1. So we're going to go right 1, put a point. And it didn't get stretched or shrunk at all. So you can use 1 as your slope. You're going to go up 1 over 1 in each direction. So, oh my gosh, what happened on the left side there? Yeah, that's going to connect. Now, I think I can't go past 2. 2 is right here. Do I want an open or a closed circle there at 2? For 2, it should be closed. Hold on, because I heard people saying open. I know exactly what you were looking at. At -3, it technically should have been open, but why is it closed? Yeah, because the other one was closed and they connected. If they connect, it's just going to be closed. So it should look something like that. All right, and then the last piece is square root. It's going to do something like this. Just act it out. We're going to start by plugging in 2. But Miss Cole, you can't plug in 2. Yes, I can. It will be open. All right, here, I'll just make a little table for us. if you plug in 2, 2 times 2, 4, square root of 4 is 2. So you get 2, 2, but it's open. Now this is a little tricky. You have to find another number bigger than 2 that you can plug in, and so it'll actually work out for you without a calculator. So like, think about it. Like 3 is not going to be good. 8. I think that'll take us right to the edge. 8 times 2, 16, square root of 16, 4. Good. So we get 8, 4. I think I'll make the grids 8 by 8, so it might be right on the edge. Yeah, so 8, 4 will be right there, and it's going to do something like that. So we're going to do the same 3 things. We're going to do domain, range, and then continuous or discontinuous. So just watch me point to it for domain and range. As we sweep left to right, what do you think? This is like scanning, scanning, scanning. Do we get everything? Yes. This piece picks up where that one leaves off. So, I mean, we get it all. Negative infinity to positive infinity. The range won't be everything on this one. There is no graph down here. As we scan from lower numbers to bigger numbers, like an elevator going up sort of, what y value do we start at? Good, thank you for not saying 1. It's 0, and will it get a bracket or a parenthesis? Well, is there an actual point there? Yes, so it will be a bracket. Now this is tricky too. I know it, now this is just constant, but I know it looks like this side is not really in a great big hurry, but it's gonna go off the paper and like off the desk and down the hall. I know this is not in a great big hurry, but it's gonna keep going that direction forever. So if it keeps going up forever, we'll still put infinity. I know it doesn't look like that, but an arrow means it's gonna keep on going. So it will be infinity. I know it doesn't really look. And then the last thing was continuous or discontinuous. What do you think? Discontinuous, is it removable or non-removable? Good, because it's an actual jump. So we're going to say non-removable discontinuity. You can abbreviate at x equals, and you always have to say the location. Good, 2. You guys are doing good. Nice job. All right, let's try this one. Where's our cut point? 1. Good. So it's going to get cut like right here if you want to almost like indicate it for yourself. What kind of function is the first one? Okay, what do I call that shape? I just always go like this. The swoop. Okay, let's make a table of numbers and plug some stuff in. What do you want to plug in? 1 is good. And what else? And 0. Whoever said 2, you're not like wrong, but why can't I plug in 2? It would be above 1. So it cuts at 1. We can't go there, but we can do 0 and 1. All right. So if you plug in 1, 2 to the 1, 2 to the 0 is 1. So those are your points. We need to be careful with our circles though. 0, 1 is just like any old point. So that's fine. But 1, 2, 1 is our cut point, and that needs to be what? Yeah, that needs to be open. So 1, 2 is going to need to be open. And it's going to level off at 0. That's your asymptote, and it'll look like that. So it would be a whole swoop, but we just amputated it. So it would do this if we drew the whole thing, but we just cut it off right there. And then what is the second function going to look like? That's not exponential. That would be, I heard somebody say it. Linear, good. Slope is -1, good. I would still plug in 1. It would need to be an open circle. But if you plug in 1, -1 plus 3, be 2. Oh my gosh, that's right here. So they do link together, but why can't I fill this in? It's still not equal. Usually when they link up, you can fill it in, but we can't for this one. All right, and then you can make a table and plug in more numbers if you want, but I would just do the slope down 1 over 1. It's a -1 slope, so it'll look like that. And we're going to do the same 3 things: domain, range, and then discontinuity. So this domain's a little tricky. Watch. It goes forever to the left and it goes forever to the right. But as you scan, who is not invited to the domain party? Who got left out because we skipped one? One did not get invited. Does anyone remember how to write it? We went over one of these, so if you don't remember, that's fine. I just want to see if anyone remembers. There will be a U in it. 1, good. Union. Good. Nice job, guys. You want everything left of 1, everything right of 1, but not 1. 1 is not invited to the party. Cool. That's awesome. All right. And then range, you're going downwards to upwards. So again, just watch me point to it. We're scanning. This goes down forever. So it'll be -infinity up to what Y value? 2. Good. -infinity to 2. Y a parentheses, open circle. Oh, nice job, guys. That was good. You guys are quiet, but you're paying attention. Cool. And then continuous or discontinuous? Okay, but which type? Good. You guys are awesome. Removable discontinuity at x equals 1. Nice. Makes my job easy when everyone's like answering. Oh, I'm so excited. You guys are getting it. Cool. We're going to do one more and then we'll do a break. Because then we'll be finished with the graphs and you'll all be happy. You'll be like, we're done graphing for today. All right. When you say something like this, that means you want this function at literally every number in existence except 3. So in this case, I would graph the whole thing and just erase 3. If you're writing with pen, maybe wait till I finish, because you want to do that graph everywhere except 3, okay? So what would that graph look like? Just plain old X. Line, +1 slope, and we'll start where? 0, good, origin, perfect. So start there, up 1 over 1. You can count to 1, you can do it. And there's your line. Again, if you're writing with pen, maybe wait till I finish this because we're going to erase. So you want that everywhere except 3. And so I'm just going to go to 3. What are you doing? No, let's teach you. Oh, that's fine. I'm so sorry. We're going to have to get used to that. All right, so just watch me do this. Do you see how 3 is right here? I'm going to find that on the graph. I'm going to literally just erase it and put what in its place? Good. Yeah, we're like literally just taking that out. And then where am I putting it? It's like I thiefed it from right there. And then where am I taking it and putting it? Yeah, like at -2. So it's that floating point. It's like, haha, tricked you. Points down here. Go ahead and enter that and I'll hit the green button on it. And so we're going to do the same 3 things. So what do you think for domain, left to right? Yep, all reals. We got everything. I know it kind of doesn't look like it, but where that open circle is, we still have that point. So as you go to left to right, you didn't miss out on anything. So you still got that point. It's just somewhere else. Range, that's not going to be the case. So look. Scanning. Who is not invited? 3. There's not a point somewhere else to make up for it. So 3 is not invited to the range party. And then the last thing we did is removable or non-removable. Removable discontinuity at x equals 3. So for these 3, we have the graph, we're gonna write the equation. So it's the opposite of what we just did, where I gave you the equation and we drew the graph. We're gonna do that backwards, all right? So I left the space here where I'm just gonna put like A, B, and C, because the graphs take up so much room on the paper. So here's my suggestion for the first one, or for any of these. Put your f of x equals and draw your swirly bracket. And don't get hung up on drawing a swirly bracket, because I always get people that are like, I can't draw one of those. Then just draw a squiggle. I don't care. All right. Here's my suggestion. Decide where the cut point is first and do that part first, because that will make the rest of it a whole lot easier. So for letter A, where is the cut point? Where did it get split? At -1. Do you guys see that there? So the first portion, I'm just going to leave this blank a little bit. The first portion, I want everything smaller than -1. And the second portion, I want everything greater than or equal to -1. And do you see how I put the equal to on the one that has the closed circle? Are we good so far? Decide that part first, because I think that makes it a whole lot easier. Now we're going to go in and fill in the blanks. So let's do the equation for the first part. First of all, what's the parent function? It's a u, so it's what? It's quadratic. What's been done to it? Good. So we're going to need a negative. And then it also, instead of having that center point at the origin, it went what direction? Good. So that needs to be inside of the function. And it's kind of backwards. What would go in there? Yep, x plus 3. And do you notice how I put a squared? It's because it's quadratic. And then we're going to do the second part. That's linear. So it should look like y equals mx plus b. What's the slope of this line? Like how much up and over is it going? Yeah, do you see up 1 over 2? 1/2 slope? Okay, so it'll be 1/2 x. And then where does it hit the y-axis? Is that -5? And that's it. You just fill it in with the equations. That's your answer. So I would decide how it splits first, like do this part first and then go back and write the equations. In my opinion, I think that's the easier way to go about that. You can, of course, do whatever you like. All right, letter B. Put f of x equals, draw your swirly bracket. Now we're looking at this one. This one's broken into 3 pieces. Let's split it apart. Let's do the, like where the cut points are first. What's your domain for this first portion? Yeah, to -2. So we would say x is less than or less than equal to? Yeah, good. Less than equal to -2. And then the middle portion is from -2 to +3. Here's how that goes when it's from here to here. You put the -2 on the left, the +3 on the right. X goes in the middle, and your little alligator mouths eat left to right. Do you remember when your elementary teacher was probably like the alligator wants to eat the bigger number? I mean, all these years later, I still got nothing better than alligator wants to eat the bigger number, okay? Just make sure you're careful. We want an open circle on the -2 and a closed circle on the 3. But left to right is how you want to do that. And then what's the domain for the third part? Yeah, good. So it would be x greater than 3. Perfect. Split it up first is my suggestion. Now let's go back and write the equations. So what's our parent function for this part? Absolute value. And the center, instead of being at the origin, how did it move? It went like what directions? Yeah, left 4, down, good. So it'll be absolute value x plus 4 minus 1. It didn't get stretched or shrunk at all. It's still like up 1 over 1 for the slope. So it's still like we don't need a vertical stretch or shrink or anything. All right, the middle part, you kind of catch a break because it's constant. What are we going to put for that middle piece? Yeah, like literally just the number -2. I always like the constant bits. I always feel like, oh, I caught a break there. And then this last one's linear. It should be y equals mx plus b. This is a little tricky though. What's the slope for this? It's -1. So you have -1x plus, watch me points to this. You have to figure out where it's going to hit the y-axis. So if you continued this on, you're going to have to use your imagination. If you made it keep going, where would it hit the y-axis? At 3, so plus 3. So -1x plus 3, or just -x plus 3. So it is y equals mx plus b. It's just you had to figure out what b was. You had to make it keep on going. And then C is one of those, haha, tricked you, the point is somewhere else now kind of things. So that's going to be like number 4. If you want to look back at number 4, you want one equation for literally everywhere except a certain number. And then you want something else when x equals that certain number. Well, what is that certain number for this one? -1. Okay, so you want one equation for everything else, and then one equation for -1. And it's nice because it's constant. The rest of it's constant. So where are we constant at for everywhere else? -2, like literally just the number -2. But where is the floating point? Like where did we stole it and we took it, and where did we put it? At +2. You just like took it out and put it at +2. Do we remember how to evaluate? Because I wrote that as a note to myself to remind you guys how to do that. Let me make up a couple just really fast. All right. I would suggest you write them down, but if you don't want to, I guess I can't force you. Let's look at graph A. Do you remember how to evaluate these? Like if I asked you to evaluate f of -2, do you remember how to do that? You would look at -2 and find where that hits the graph. It's like the point -2 comma whatever. So where would that be? Do you guys see that there? How about f of -1? Like where the cut point is. Where's your actual point for -1? Like the filled in one. Yeah, what do I want to call that? Like -5.5. But do you guys remember how to do that? Like find it on the graph? Okay, just checking. And then the last one's on there. Find A so that the graph will be continuous. What that means is you want the two pieces to do what? Meet up, right? So that means, like intuitively, what do you think you want to do with these two things? You want them to meet up. What should you do with them? If you want them to meet up, what should you do with them? These two things right here. What should we write on our paper? Make them equal each other. Very good. I knew we would get there because it should make sense to you. So you're going to take that thing and make it equal that thing. Like you just take them and slap an equal sign in between. And then you plug in for x. What number do you think? Good. Plug in -3 for x. And after that, you just solve it. All right. So we're going to plug in -3 wherever there's an x. So if you want them to meet up, set them equal, plug in whatever the cut point is. All right, here we go. -3 squared. Good. 9 times 5, 45. Good. We know our times tables. 45 plus a equals -9. Perfect. And then what? -45. What is that? -54. And we're just going to try that again. I think I threw a squared in this one though, so be careful. You want them to be continuous? You're going to take this and make it equal that. So 2a squared plus x equals the other thing. I'm not going to read it to you because that's annoying. Just take them and put an equal sign in between. And the other thing that's a little tricky about this is you have to plug in for x, not a. Like I get that there's two different variables going on there. So Make sure you plug in for x. And what number are we plugging in for x? 2. Okay, so it's going to be 2a squared plus 2 equals, and then on the other side, we're plugging in 2 for x. So 3 times 2, 6 plus 7a. I'm not going to question you on this one. I'm going to just assume that everyone's probably forgotten this because usually that's the case. So I'll just go through it. Whenever you see a squared, or if anyone does remember how to do this, I'm going to be super impressed. Whenever you see a squared, you need to move everything all to one side so it all equals 0. I call this evacuate. When you see a squared, evacuate, evacuate. You're going to bring everybody over so that it all equals 0. And what you want to do is make it be something squared, and then like something a, and then just the number. Okay, so let's see what we've got. 2a squared minus 7a, you want to put that in the middle. And then what? What's our leftover number? That bless you. -4 equals 0. I will question you here. Do you remember what to do after that once you get it all evacuated? Yeah, does anyone remember what that's called? Factoring. Good job. I'm going to expect you guys to be better at factoring than my classes last year, because like factoring kind of hit them during COVID, but you guys learned it. You're on the hook for this. I'm not letting you off the hook for factoring. All right. What multiplies together to equal 2? 2 times 1. So 2a and 1a. 4 would be 4 times 1 in this case. And I usually just have everyone check the outsides and insides. The outsides would give you 2a. 2 times 1 is 2. The insides would give you 4a. Oh, 2 plus 4 won't be 7. So I guess I have it backwards. Let's try it the other way around. Try again. Now what are the outsides giving you? 2 times 4, 8. And then the insides, 1, which will get you to -7. You would need a -8 plus 1 will get you 7. Don't throw your pencil down yet, because that's not actually the answer. You have one more step. And in fact, there's going to be how many answers? 2. There's going to be 2 answers, 1 for each of the factors. So you get a equals, what do you get if you set this equal to 0? And it's pre-calc, so it's a little advanced, and I kind of coach everyone to try and do this in their head. If you set this equal to 0, you would negative the 1, so subtract the 1 over -1, divide by 2. And if you set this factor equal to 0, you would get 4. So 2 answers for that one.